Okay, so I'm going to start to give some consequences or more properties of the eigenvalues and eigenfunctions. I'm not going to. These are in chapter 7 of the notes. I'm not going to prove all of them. I'm going to prove the ones that I think. Well, some of them just take a long time to prove. I'll mention them as we go along. So, the first thing that I want to prove is using the properties from the previous videos. I want to show that eigenfunctions corresponding to different eigenvalues are orthogonal. That is, their integrals are equal to 0. And the integral is going to be relative. It's going to be a weighted integral, and sigma here is going to be the weight. So you have the following lemma. So by the way, if you have, well, you've all taken linear algebra. I forget which class I'm talking to sometimes. You've taken linear algebra, so this is a very generic fact. Anytime you have eigenvectors corresponding to different eigenvalues, we're going to have this orthogonality. Okay, so what we're going to have then is if, and assume that, I'm not going to write everything, but assume that phi and psi satisfy these boundary conditions. So if we have L phi is equal to minus lambda sigma phi, and L applied to psi is equal to minus gamma sigma psi, then either, and these both could be true, either lambda is equal to gamma, or the integral from a to b of phi times psi, and again we're integrating relative to the weight sigma, this is equal to 0. Okay, and so let me just give this argument. So I want to know something about this integral here, so that's what I'm going to do. I'm going to start by computing the integral from a to b of phi psi sigma. Well, what do I know about psi? I know minus gamma times sigma times psi is equal to L psi, so if I just look at sigma psi, this is going to be equal to minus 1 over gamma times the integral from a to b phi L psi. Now I'm going to use the symmetry of the operator L. This is minus 1 over gamma times the integral from a to b psi times L phi. But what is L phi? Well, L phi is minus lambda sigma phi. So this is lambda, and L phi, well, the minus lambda was there, so this is just going to be phi sigma. Well, this integral and this integral are equal to each other. So how can this happen? Well, if this is equal to 0, and that's equal to 0, that's one way this can happen, so that takes care of this. If lambda and gamma are equal to each other, this is also going to be true. So if lambda and gamma are not equal to each other, lambda over gamma is not 1, and so the only way this can be equal to each other is if the integrals are equal to 0. Caveat is if lambda is equal to 0, this doesn't work, and if gamma is equal to 0, this doesn't work. So now what I want you to do is you need to figure out what happens if one of lambda or gamma is equal to 0, but I'm not going to talk about that. That's something that I want you guys to think about on your own. Okay, so this next thing I'm definitely not going to prove, but it's important. So just like with these sine and cosine functions, which are the prototypical examples of solutions to the Sturm-Liouville problem, just like we can expand any function in terms of sines and cosines, we can expand any function in terms of these eigenfunctions as well. So in particular, let me say sort of two things. So if we have some function f of x, and we know it is a linear combination of the eigenfunctions, so k equals 1 to n ck phi k of x, and we're going to assume that we have normalized things so that the integral from a to b of phi k star of just not phi k star, phi k squared. I don't know where star came from. So we're just going to divide the phi k's by whatever we need to get this normalization. Then ck is equal to the integral from a to b of f times phi k, and this is going to be relative to the weighted inner product with the weight sigma there. Okay, so you should be able to prove this. This is just the orthogonality relationships. So it's a very generic fact about about computing these coefficients when the phi k's have some sort of orthogonality property, and I will let you figure that out. But the second thing that we know is that so this is for the case where f of x is given as a linear combination of the phi k's, but in general, as long as f of x is piecewise continuously differentiable, we're going to get that f of x plus 0 plus f of x minus 0 over 2. So remember, this is the average of the left hand and right hand limits. This is going to be equal to the sum k equals 1 to infinity ck phi k of x, where the ck's are defined by this up here, by this same formula here. So again, this is very similar to what we saw for sine and cosine functions. We can expand our function as a series of these phi k's, and if f is continuous at x, f of x is just equal to that. Otherwise, if there's a jump discontinuity, it's going to converge to the average of the jumps. And this is something that's going to be very important for us when we start to use these functions to solve PDEs, or at least to sort of think about solutions to PDEs. I'm not going to write it down, but I am going to say that for these problems, the eigenvalues are real. So if we know that we have these boundary conditions and this differential equation, and if P and Q and sigma are all real, which is one of the things that we're assuming for a regular Sturm-Liouville problem, then all of the eigenvalues are real. And this is something that is in the notes that you can look over. Furthermore, it's not true that the eigenvalues are necessarily non-negative. So we could have situations, especially, not especially, but if Q is negative, we could have situations in which the eigenvalues are negative. So exercise 7.10 asks you to think about this a little bit. But limit 7.11 says for a Sturm-Liouville problem, there is a smallest eigenvalue. Actually, I need to be writing this. There's also a typo in the notes that I need to fix. I say basically the exact opposite of what I should be saying. Okay, so for a regular Sturm-Liouville eigenvalue problem, there is a smallest eigenvalue, lambda 1, and the eigenvalues are infinite, and there's infinitely many, and there are, I'll just write it like this, infinitely many eigenvalues that can be ordered as like lambda 1 is less than lambda 2 is less than lambda 3, and so on and so forth. So what this means, I mean, smallest eigenvalue, smallest here, maybe smallest isn't always the best term, but lowest is also ambiguous. So sometimes smallest can mean like closest to 0, meaning the absolute value, but that's not what I mean here. I mean there's a smallest eigenvalue as in like there's no eigenvalues less than. So you could have negative eigenvalues, but there's not going to be eigenvalues going all the way down to minus infinity or unboundedly going down to minus infinity. There's going to be some lowest eigenvalue, and then we can order them. So there's one that comes after that. There's a well-defined next eigenvalue that comes after lambda 1. So lambda 1 is the smallest eigenvalue, and then there's always going to be a well-defined eigenvalue that comes after lambda 2, and there's no after lambda 1, and there's no eigenvalues that are between lambda 1 and lambda 2. So in other words, it says we're not going to have any situation in which 0 is an eigenvalue, and then the next eigen, we're not going to have a situation in which the eigenvalues are of the form like 1 over k, as k goes from 0 to infinity. Like, it's not going to be 0, 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. So it's always going to be like this discrete space between each eigenvalue. So we can order them in this way. So I'm not going to give you the, so actually I will begin kind of discussing why this is true in this video, because it gets us to something called the Rayleigh quotient. But I'm not going to prove it, but you should definitely read the proof. The proof involves a lot of it involves a few interesting things. But I'm going to let you guys read the proof of that. So what we're going to start with is we're going to look at the integral from a to b of phi squared sigma, and we're going to multiply and divide by lambda, and this is going to be lambda. Actually, I think I'm going to have 1 over lambda on the outside here. This is 1 over lambda times the integral from a to b phi lambda phi sigma. Now if phi is an eigenvalue and lambda is a corresponding eigenvalue, if phi is an eigenfunction and lambda is a corresponding eigenvalue, we can simply write this as minus 1 over lambda times the integral from a to b phi L phi, because lambda phi sigma is going to be minus L phi. Well, if you think back to the video that I made where I had that symmetric property psi L phi minus phi L psi, we have a similar format here, except instead of psi L phi, it's phi L phi. And so what we're going to have, I'm going to scoot this over, we're going to have minus 1 over lambda, and on the inside we're going to have the boundary terms, so p phi prime going from a to b, and then minus the integral from a to b. P, in the previous video it was p times psi prime times phi prime, but here psi is equal to phi, so this is just going to be phi prime squared, and then minus q times phi squared. So now if I look at this, I can solve this for lambda. And when I do that, I get that lambda is equal to p phi prime. We're integrating from a to b, excuse me, minus the integral from a to b of p times phi prime squared minus q phi squared. Then I'm going to divide by, there's a minus sign here that I have, let me fix this. So there's a minus sign here that I'm going to distribute. When I distribute the minus sign, that becomes a minus. This becomes a plus. Minus minus is plus, and then when you hit it with the minus, it goes back to being minus. So it's like this, and then we divide by the integral from a to b phi squared sigma, like this. This is what lambda is equal to. So if phi is an eigenfunction, then lambda is a corresponding eigenvalue. And so, if phi is an eigenfunction, lambda satisfies this equation where lambda is a corresponding eigenvalue. Okay, so let's notice a few things here. If we're dealing in a situation in which the boundary values are 0, this goes away. So we don't have this term anymore. If q is negative, notice if we don't have this, like if we're dealing in a situation like where phi of b is equal to 0, or phi prime of b is equal to 0, or phi of a is equal to 0, and phi prime of a is equal to 0, we no longer have this term. In those situations. Now that's not going to be the case in general, but that's what in those situations, that's what we have. This is equal to 0. In addition, if Q is negative, then what it's saying is that this is going to be positive. If Q is negative, this integral is going to be positive because phi prime is positive, P by assumption is positive, and phi squared is positive. So if we're dealing with like very simple Dirichlet or Neumann conditions or even mixed versions of those, this goes away. And if Q is non-negative, if Q is non-positive, then this is going to be a non-negative term, in which case we see that lambda is going to be greater than or equal to 0. Okay, so in the case of Dirichlet or Neumann or mixed Dirichlet-Neumann conditions and a Q that is non-negative, which is typically going to happen, well, which is, you can look in the notes, this is a very physical, reasonable thing in many situations. This is going to be non-negative. Now, to prove that it's going to be non-negative in more general circumstances, let's forget about this. Let's still assume that's equal to 0. But if you want to deal with a situation in which Q might be positive or might be negative and positive or whatever, you're going to have to estimate this. And what you're going to have to do is you need to somehow compare the phi squared with the phi prime squared. That's basically going to be what's going to have to happen there. Now, to do that, you're going to use something called Poincaré's inequalities, or a Poincaré style inequality, which is a way of estimating phi in terms of the integral of phi prime. Now, I'm not going to go over that in this video. If you want to read it in the notes, I think that would be great. In fact, I highly suggest you recommend going over the proof of this. If you look at page 97, there's limit 7.11, and then I continue on page 98 where I actually give the proof. I want to talk a little bit about something else here, but go over that, ask about it in the discussion forums if you want. But what is true is that this quantity right here on the right-hand side of lambda, if phi is an eigenfunction, then this quantity is equal to the corresponding eigenvalue. But we can actually view this just, phi doesn't have to be an eigenfunction for us to compute this. So I'm going to call this R, and then use brackets here, R bracket phi. This is something called the Rayleigh quotient. And I'm going to mention something about the Rayleigh quotient now. So what is true is the following. I'm now stalling because I have lost my place in my notes. What is going on here? Here we go. Okay. So lambda 1, which is the smallest eigenvalue, is equal to the minimum, where this is taken over functions u. So u, I know a lot of times, is the unknown function in PDE. For now, it's just going to be a function of x. So if we take the minimum over u, continuous, that satisfy these homogeneous boundary conditions, and we're going to look at the Rayleigh quotient. The smallest of those is equal to lambda 1. So in other words, I'm going to look at all of the functions that are continuous and not identically equal to 0. If u is identically equal to 0, the bottom here is not defined. It's not well defined. The bottom is 0, so as a whole, this quotient is not defined. So minimum of u that are continuous and that satisfy the homogeneous boundary conditions. So I'm going to look at all non-trivial continuous functions that satisfy the homogeneous boundary conditions. I'm going to take the Rayleigh quotient, I'm going to compute the Rayleigh quotient of that function, and the smallest one of those is going to be equal to lambda 1. So what this means is if you take any function that is continuous and satisfies the homogeneous boundary conditions and compute the Rayleigh quotient, you know that lambda 1 is going to be smaller than that. Okay, but in using this fact, we typically don't want to just pick random functions because it's going to be minimized, the Rayleigh quotient is going to be minimized by functions that are closest to phi. So the closer your trial function here is to the actual eigenfunction, the closer this is going to be to lambda 1. Okay, well, an obvious question to ask now is, if we don't know what the eigenfunction is, how do we know what's close to the eigenfunction? Well, here is where we're going to look at lemma 7.15. So this is the next lemma. And this is something that's useful in this. See, we have to keep in mind that when we're thinking about these eigenvalue problems, hold on one second. The ones that we've seen so far have been simple, and we can compute everything very explicitly. We can compute lambda very explicitly, but that's not always the case for P and Q. If P and Q aren't trivial, aren't just 1 or 0 or something, that's going to be challenging. And even in cases when it's easy to compute the solution in terms of lambda, it can be challenging to find what lambda is. We'll go over some of that. Okay, so lemma, the eigenfunction phi lambda k corresponding to the kth eigenvalue lambda k has exactly k minus 1 zeros in the interval a to b. And notice I'm not including a or b there. Okay, so if like phi of a is equal to 0, that's not included in this count of k minus 1 zeros. So think about the functions, think about the eigenfunctions that we've looked at so far. Sine of k pi x. If you think about sine of k pi x from 0 to 1, how many zeros does it have? Well, when k is equal to 1, we have sine of pi x. Now, at 0 and 1, sine of pi x is equal to 0. So there's 2 zeros there. K is equal to 1, but we have 2 zeros. According to this theorem, there should be k minus 1. And there are 0 zeros in the interval 0 to 1 if we don't include 0 and 1. Okay, so if you think about sine of 2 pi x, that has 1 0 in between 0 and 1 at 1/2. K there is equal to 2. K minus 1 is 1. K is equal to 2, and so it corresponds. Similarly, if you look at cosine, if you look at the cosine k pi x functions, now that starts the smallest eigenvalue. So here we think about, we need to reorder things a little bit different. So lambda 1 is always the smallest eigenvalue. So for cosine, we start with cosine k pi x. Well, the first eigenfunction corresponds to k equals 0. So the smallest eigenvalue in that case, lambda 1 is equal to 0. The corresponding eigenfunction is just the constant function. So that corresponds to, that's the first eigenfunction. So there the k is 1. So k minus 1 is 0, and there are 0 zeros for the constant function 1. Then we go to cosine pi x, and there's 1 0, which is consistent. Okay. So in other words, if we want to use the Rayleigh quotient to try to compute, to try to get an estimate on lambda 1, the best thing to do then is to take a function that satisfies the boundary conditions and has no zeros on the interior of the interval from 0 to 1, or from a to b, if that's what we're working with. Okay, so I think there's a problem on the homework where I'm asking you to do this. It would be very good to pick a function that's going to look most like the first eigenfunction, or sorry, the first eigenvalue. Okay, I think that is all. Oh, sorry, one other thing that I want to mention. I'm not going to prove this for you. The proof, again, is very good. It's very instructive to look at. So I highly recommend looking at the proof of this fact here. What I am going to point out, though, is that if you go through the proof and you understand the proof, I don't think I want to even tell you. Let's see. I think I want to make you think about it. Yes, so I think I'm going to wait a little bit. Maybe I'll mention it on the discussion forums. Exercise 7.14 says, note that if you look at the Rayleigh quotient for all functions for which C1 is equal to 0, that is, if we expand a function in terms of the phi k functions and the first function is equal to 0, the C1 is equal to 0, we can prove a similar statement about lambda 2. In other words, I'll give you a little bit more. This is not the lemma. This is, if you go through the proof, you'll be able to figure out something about lambda 2. Lambda 2 is equal to the minimum, and I'm going to let you figure out what the minimum needs to be taken over, R of u. And then you can once you get what lambda 2 is, then you'll be able to see a general formula for lambda k. Okay, that's all I'm going to say for this video. In the next video, I'm going to sort of work through, in a certain sense, how we can use all of this stuff to analyze/solve a heat equation for like a non-homogeneous rod. So we're going to have like the P and Q and sigma or whatever it is are not going to just be kind of ones and zeros.